I'm good. All right. Thank you everybody for attending this today. So what I'd like to talk about today essentially is our experience with using machine learning techniques, developing, I would say, a practical spectroscopy application, especially in oncology. So I just wanted to show a disclosure because I might disclose an instrument that we commercialized. Today I might talk about this instrument. So today I'd like to initially, I'm sure I do not need to remind what spectroscopy is to this audience, but I'll just do a quick overview. Just want to discuss how we in our group are applying machine learning techniques to tissue spectroscopy. And I'll emphasize several of the challenges I would say that could lead a researcher, for example, to I would say underuse a data set when applying machine learning techniques for the development of predictive models. And then I will show specific applications of our models. So the way we're using spectroscopy really is a little bit like they do in astronomy. So we're using a sophisticated detection system that relies on a spectrometer. Typically, the spectrometer obviously is more sophisticated than a simple prism. But what we're aiming at basically is trying to identify in a full spectrum peaks, if you will, that will be associated with specific biomolecules. Like, for example, in our specific case here, light is shone onto tissue. Light will travel into the tissue, will get absorbed, will get scattered as well. Sunlight will come back. And I guess in optics, one of the features that is interesting is that we can probe light tissue at different depths by modulating the excitation wavelength, and by modulating the detection wavelength, we can essentially reconstruct in terms of different contrast mechanism the profile of a tissue in terms of the biomolecules that it contains. Could be absorbers, or in our case, what we are more interested in, at least today, will be to present our technologies that we've developed for Raman spectroscopy. Raman spectroscopy essentially puts into motion vibrational modes of the molecules into the tissue and detects redshifted light at a large number of wavelengths that is associated with light that's been absorbed, if you will, used to excite those molecular modes into the tissue. And as you look at a spectrum associated with a piece of tissue, for example, could be in vivo, it could be cells, it could be a slice of tissue. It will be composed of multiple types of molecules. It could be amino acid, it could be proteins like albumin, for example. It could be lipids, DNA, RNA, and each of those will have specific molecular profile that you can pick up. And in reality, when you look at more complex organizations of tissues and of cells into tissue, well, it gets more complicated. So the spectrum will become a roughly speaking a linear sum of a lot of molecules in the tissue. So you need to interpret this data. So that's what I'm going to talk about today, how we use machine learning to reinterpret and transform these data into something that can be useful for medical practitioners. The applications that I will go over quickly basically are surgical guidance and biopsy procedures. How can we use that information from machine learning and spectroscopy to help those procedures? And also, how can we complement the information that's provided to pathologists in order to improve the diagnostics and prognostic, reduce inter-observer variability, and potentially help resolve complex diseases. So in order to show how we're using machine learning in our lab, in our methods, I will use a specific problem to start with, which is that associated with using optics to guide surgery here in the context of neurosurgery, where it's needed to maximize the extent of tumor resections for some tumors. And here, what you typically would get when you interrogate a tissue live in vivo during the procedure, you would get, for example, a specific spectrum associated with a tissue that would contain cancer cells. just to simplify the problem, and one specific spectrum that could correspond, for example, to normal tissue. And the idea is that ultimately, using statistical methods, you could, without at this stage even resorting to machine learning yet, you could use multivariate approaches to try and see what bands are mostly expressed, say, in one category or one tissue label versus the other one. So in the case of here, I'm not going to go through details here, just to show that typically you would get that some bands are more expressed, say, in normal tissue. Some bands will be more expressed into cancer. And if you build this, you can make an association that is robust between, say, cancer and normal, and the bands, which you can then associate to molecules and families of molecules. Then you can prove, you can give some biomolecular information that is consistent with the biochemistry of a disease, for example, as here was the case, for example, in glioma. So this is for a data set for a glioma that was acquired live during surgical procedures. And the challenge for us is to transform this very complex information into a single prediction. Here, is there cancer, or is it normal? Basically, when a surgeon will apply a tool like here, it's a contact probe to make a measurement and help in guiding the surgery. So we use machine learning to automatically detect like patterns in complex data sets. And I would say that the main challenge in our approaches is to always, given sometimes the constraint of data sets, which can have a lower number, a small number of data points, for example, compared to what we should get if we were to contemplate deep learning approaches, for example, for the same kind of problem. Is to strike the challenge is to strike the appropriate balance between the complexity of our model and its predictive power, i.e., how can our model will it, and how can it generalize to new data that it will see during a surgical procedure for this to be useful. And the way we're using we're doing our machine learning is very standard, i.e., it's supervised. We assign to each measurement a label or an ensemble of labels that we can then use to train an algorithm. So the steps are we do a feature selection. We to reduce the size of the data set, which is especially useful when we have data sets with low ends. And then we test, we validate, cross-validate we make models, we train our models basically to ensure that we minimize the amount of overfitting that we're going to do. And then this is tested on independent data. So this is always what we do. And typically how it looks here, this is an example for prostate cancer, where we would take multiple measurements on an organ. And for each of these optical measurements, we would have a bunch of pathology labels that would be assigned by one or multiple pathologists, so that we can then use all of these labels. The simplest is benign cancer, but there can be more sophisticated, if you will, stratifications of the samples in terms of grade, percentage of blend, and there's multiple things that can be done. And in principle, then you can use all of these labels if you have sufficiently large number of measurements, patients, etc., to make multiple predictive models. So I would say that it's all the devil's always in the details in these approaches, and the main challenges for this is to ensure that we understand well the limitations of pathology. Like, for example, depending on the complexity of what we want to achieve in terms of detection, there can be inter-observer disagreement between pathologists. There can be an issue with spatial registration accuracy between the measurement and where the pathology is made. I mean, for different sort of optical technique, there can be issues with the depth sampling ambiguity of your optical measurements and where you actually do pathology analysis. And also, obviously, I mean, you're as good as the pathology or whatever methods are used to pre-qualify the measurements. So disease complexity and undetectability with standard methods, it can be an issue, obviously, in making new models that can be useful. So for us, the key is, as I said before, is feature selection. So feature selection means that you will dimensionally reduce your data set. This could be for Raman spectra, you could use the width of a peak, for example. You could use the height of a peak. You have multiple data within a spectrum associated with all of these. But there's also other interesting aspects of these spectra that can and need to be considered. Interactions between the peaks themselves as variables, which because they're not independent, the different peaks. And also something we've more recently started to look at. And here there's an issue with my, there's supposed to be another image here, but that's okay. Give me a second, that's all right. So something that we've started to consider more is having interactions between our optical data and, say, for example, a patient age. For brain, for example, biochemistry of the brain changes with age. So this variability, we don't want this to act as a confound factor in our predictive modeling. So we can account for the interaction of age with our optical variables, Raman in this case, sex, ethnicity, etc. And there could also be suppose this tool is used for during a surgical procedure. Well, there can be results that were obtained before the procedure's blood test, for example, that could be used and made to interact with our variable, basically to improve predictive accuracy. So the methods we're using for machine learning, there's a layer, a pre-training layer of feature selection I've described before. There's multiple ways to do this, but here I'm just showing approaches that we've developed using support vector machines. And typically we do the feature selections, we train, we test on an independent data set, and so assessment of performance is done using RC curves. And what is the end result specifically for this example that I was talking about for brain surgery with the NL probe? The result is a model that generalizes to new data. In the case here that you see, here, this is to the left, this is a tumor that was resected, and where the probe, for example, in this case, was saying that there was residual cancer at the boundary where the surgeon would have stopped resecting, continued, and got to a point where it was all normal. And then all this was sort of was validated with pathology to show here. This is I would say that the best case scenario for how a technique like that with a good model can really help maximizing the extent of resection. This was for a low-grade glioma patient here in Montreal. And there are several potential issues, if you will, or things that need to be that we need to worry about when designing good models and making sure they can be applied later practically. Data quality is very important. So when you do a data acquisition in the OR, your model can be super good, but if you don't ensure that your data is properly has sufficient quality, and also that your calibration and normalization is such that you can actually use a model that was trained on data in Montreal on data that's acquired in Japan, for example, well, those can all be issues. So we've worked out these details over the last a few years for rapidly. I mean, in terms of data quality, well, one of the lessons is that you need to know your data well, right? Because ultimately, you need to be sure that whatever you're going to feed to your model is going to have at least a data quality that is equivalent to what was used in our case to train the models. In our case, what we did, we developed an approach that ensures that there's always a sufficient signal to noise ratio within the Raman photons that are collected to make sure that for tissue, we can always get the specific tissue peaks that are always there into tissue. I want to go into specifics, but this is just to illustrate that it is very, I mean, there are sort of prerequisite steps to this that are crucial to clinical translation. And I think another thing as well is this compatibility of the data between imaging systems, which will ultimately result in ensuring that the models are portable across systems. Here, just to demonstrate 9 different, here was a probe system were used to acquire data on the same tissue phantoms. And if you just look at the data without calibration, obviously it looks like a mess. But once you're calibrating things correctly, then you see that your data overlaps, and we've demonstrated that this actually also translates into a model portability. So although I'm not going to go into the details here today. So just quickly, this model portability ensures, for example, that we can develop other applications where, for example, we could train models with our NL Pro, which is easier because you can train the models basically in open surgery. But then if you want to develop an approach where you will guide, for example, the collection of biopsy specimens in the brain, it could be very tedious to have to train a model using a needle like this one. So you can use the same model you've developed with a NL probe during surgery to then ensure that a sample during needle biopsy would be collected in the tumor, for example. And so this a similar workflow has been developed for prostate cancer, where in this case we've developed a probe that's EM track, electromagnetic tracking, basically, and the position of the Raman probe is spatially registered with a live ultrasound, which is then registered to an MRI, and this allows basically to check ensure the proper targeting of where we take a biopsy specimen, and later on this will be used to help in optimizing brachytherapy applicator application. So that's one application. Another application was, there's supposed to be a video here, I'm sorry, but we've developed also these systems, and portability of the models allows these applications to be used well. We've developed these systems where a robot basically can grab a probe and interrogate tissue during radical prostatectomy procedures. This is another project we developed. And I would say that the one of the interesting projects we've done lastly was a line scanning Raman imaging system that can image over a centimeter field of view. And in this case, we've demonstrated that a model that was trained to detect, in this case, it's a little bit trivial to do that, but it's a toy model, we demonstrated that we can train a model with the probe for detecting gray versus white matter in the brain, and then use that model on a pixelized basis using this optical system, demonstrating we can reconstruct the margins between white and gray matter. This is preliminary data towards imaging cancer. And one last application that we've developed with machine learning applied to Raman spectroscopy was an aid to pathology, where Raman spectra are acquired along with visualization, if you will, of TMAs, or just basically H&E slides. And the predictive results that we're providing here are for detection of cancer versus benign lymphocytes detection. And also the most interesting thing here was able to detect a complex disease manifestation called intraductal carcinoma of the prostate. And these models were all trained in about 300 patients and tested independently in 100. So that's sort of that is the whole workflow of our methods is represented here with a large data set. So to conclude, a few, so I would say, a few take-home messages. So label-free optics has potentially large informational content, but can be underutilized if you're not careful about ground truth accuracy, data quality, model portability, confounds. Some optical problems can only be explored with machine learning approaches because of data complexity, like number of variables and self-interaction with clinical variables, which are very difficult to consider without machine learning type approaches. And small data set can only be used should be used with care for proof of principles study, feature selection, avoid overfitting when reporting, and strive to get large numbers, which is a bit obvious, but very important. All right, thank you very much. I just want to thank everybody in my lab, and also the sponsors that allowed this work to be possible. Thank you very much.